Deep-sea underwater volcanoes located between tectonic plates create a phenomenon known as hydrothermal vents. Hydrothermal vents, which essentially are underwater geysers, were discovered by the scientific community in 1977 while exploring an oceanic ridge near the Galapagos Islands. Scientists expected to find barren land due to the abiotic factors present in this biome. First and foremost, the average hydrothermal vent's depth is 2,100 meters, which translates to roughly 1.3 miles. This is beyond the reach of sunlight, which prior to this discovery was believed to be a necessity for all life to occur. Needless to say, hydrothermal vents are largely unaffected by precipitation due to the fact that they are always completely submerged. Additionally, the water in this biome has a pH of 2.8 due to the abundant presence of hydrogen sulfide dissolved into the water, a toxic compound for most organisms. There is a high salinity because the water is supersaturated with minerals such as iron, barium, and calcium. The temperature of the water that emerges from the hydrothermal vents may reach temperatures over 370 degrees Celsius, which translates to roughly 700 degrees Fahrenheit. The water doesn't boil due to the extreme pressures present at these depths. These temperatures have an incredible difference when compared to the ambient water, whose temperatures are approximately 2 degrees Celsius or 36 degrees Fahrenheit. Despite all these conditions, there is still an abundance of life present in this biome. However, before addressing the biotic relationships, I will dedicate myself to a question you all must be dying to know by now, which of course is, how do hydrothermal vents work? Well, let me tell you. Water seeps through the cracks or fissures in the Earth's crust, dissolving metals and minerals as it goes throughout its journey. As the seawater is being heated by magma chambers, oxygen, magnesium, and potassium, for example, are removed. As the water travels deeper, it picks up copper, zinc, iron, and sulfur from the crust dissolves. After going through this process, the vents spew out incredibly warm water. When it collides with the much colder surrounding water, hydrogen sulfide is created and minerals precipitate in the forms of chimney-like structures. Some of these chimney structures can reach heights of up to 60 meters or 197 feet. The smoke created through the precipitation of minerals is either a nuance of black or a nuance of white, as those are the two types of vents. Black smokers, as they are called, are the hottest vents. They are the ones whose temperatures reach around 700 degrees Fahrenheit, and they spew out seawater containing dissolved metals and sulfur. The world's deepest known black smokers are located in the Cayman Trough, which is 5,000 meters or 3.1 miles below the ocean's surface. White smokers are slightly cooler. Their temperatures usually reach between 480 and 570 degrees Fahrenheit. They spew seawater containing barium, calcium, and silicon. Instead of the barren land which scientists were expecting to find, they found communities of shrimp, crabs, tube worms, clams, slugs, and fish. But wait, there's more. Barnacles, sponges, octopi, and coral too. These rare geological features turned out to be an oasis on the otherwise sparsely inhabited ocean floor, with a biomass equivalent to that of a rainforest. No plants are present due to the absence of sunlight, which was previously mentioned. The organisms that inhabit the hydrothermal vents are unlike any other life on Earth. Instead of sunlight, they rely on the hydrogen sulfide created through the vents. In a process called chemosynthesis, certain bacteria create carbohydrates through consuming the hydrogen sulfide. This bacteria reside within many of the organisms. For example, they live in the tube worms present in the biome. Through mutual symbiosis, the bacteria is given a home, and in return, the tube worm receives chemical energy. All vent life is dependent on these bacteria, which are the primary producers in their biome and respective ecosystems. Vent microorganisms are unique in other ways too. They can survive temperatures of up to 113 degrees Celsius, 235 degrees Fahrenheit, the highest temperature recorded at which an organism can live. Even larger animals such as tube worms can live at 80 degrees Celsius or 176 degrees Fahrenheit, which is much higher than any other animal. Aside from the hydrogen sulfide, the water amongst the hydrothermal vents also contains poisonous heavy metals and is more acidic than vinegar. To this day, biologists still don't know how exactly vent animals can survive through these conditions. More than 300 species have so far been identified in deep-sea hydrothermal vent ecosystems, of which over 95% are new to science. Many of these species are restricted to an individual vent field, making many ecosystems unique. On average, a new vent species has been discovered every 10 days since vent ecosystems were first discovered in 1970. Vent ecosystems have changed very little over time. It appears that much of the life amongst the vents are closely related to ancient animals. Researchers have speculated that life initially began in extreme environments similar to that of the hydrothermal vent. Since hydrothermal vents were discovered not too long ago in 1977, in that they are difficult to reach being so deep beneath the ocean surface, they have remained more or less unharmed. With only a handful of submersibles being capable of descending to these depths, the vast majority of vent ecosystems have been able to exist undisturbed for extended periods of time. Taking that into account, it is incredibly difficult to determine which of the species present may qualify as endangered or not. Some organisms are unique to an individual ecosystem, and many species have yet to be discovered. With limited access and knowledge, we cannot successfully determine if any of these species amongst the vents are endangered or not. This, however, may change in the near future. Due to the abundant presence of metal and minerals, the concept of mining the seafloor was quickly born. Not literal mining, rather gathering the material that has settled on the bottom of the seafloor around the vents. Pound for pound, the seafloor has more ore in terms of gold, zinc, silver, and copper than land deposits. The potential annual yield of copper, if extracted, is projected to be in the billions of tons. These materials are all valuable, but not necessarily profitable considering the circumstances. Today, there are two companies who are in the late stages of developing submersibles who can cost efficiently and effectively gather these resources. They have yet to do so successfully, and therefore the human impact remains minimal to none, which leaves the biome intact and the species